In this video, we're going to use Sentinel-1 data to map flooded areas, and we're going to do that by applying a very simple technique, combining an image acquired during the flood with an image acquired before the flood to distinguish between flooded areas and permanent water bodies. In disaster mapping applications, the image acquired during the disaster event is referred to as a crisis image, and the image acquired before is referred to as the archive. So first we will open the images by selecting the two original Sentinel-1 images in their zip format, selecting them and dragging them and dropping them into the Product Explorer window. And we can see that the images were acquired in 2015. One was acquired on the 20th of March, the other on the 4th of September. So the 4th of September image is the crisis image, and the 20th of March is the archive. If we go to a map of the world, we can see that these images are over a part of Myanmar. So let's have a look at the images. If we expand the bands folder and double click on amplitude, then we can open the images in a viewer. So here we have the archive image, and here the crisis. So in the crisis image, the flooded areas are very obvious as patches of a low backscatter return. Now these dark areas are due to specular reflection over the smooth water surfaces. So the signal gets reflected away from the sensor, whereas the surrounding land is much rougher. And in fact we can see even an area of mountains here where we have very rugged terrain, and in fact we see a lot of distortion due to the layover and foreshortening effects. So what we will do is first to take a subset of the areas where the flooding is likely to have taken place, so around the river. Then we will apply a multilooking in order to reduce the speckle, reduce also the dimensions of the image, and speed up the processing time. Then we will apply a calibration, which is essential to compare two images. So we will go from digital numbers to a physical quantity, which in this case is sigma naught backscatter. Then we will do a terrain correction to project the images onto a map system and also correct for the distortion due to the terrain. And then we will combine the images and create an RGB composite in order to distinguish between flooded areas and permanent water bodies. First of all, let's view the images side by side. So we select window, tile evenly. And both images were acquired in the same geometry, so we can even see from the metadata of both images that the images were acquired while the satellite was ascending. So here we can see they're both ascending, and they both have the same instance angle, which is essential for flood mapping. But what we notice is that there is a shift in azimuth, okay? But this doesn't trouble us so much because the geometry is the same, and we can cut the images to include common areas in both. So here we will select the area where most flooding seems to have taken place, and then we will go to raster, subset, and we will take a subset including the extent of the viewer for both images. So first we have taken a subset of the crisis image, now we will take a subset of the archive by selecting the viewer here, then going to raster, subset, and then selecting OK. These have been saved just to a virtual file, so we do not have a real file here of the subset, but what we will now do is to save these to file. So we'll convert them from virtual images to real images. So we go to File, Save Product, and we select Yes. And here we can decide an output file name. So let's remove some parts of the string of the long file name that maybe we don't need, and let's keep only the image acquisition date, the sensor, the imaging mode, the polarization, and the processing level. And we'll create a suffix here, underscore crop. Then we can do the same for the other image. We go to File, Save Product. We select Yes to convert to beam die-map format. And then here we take out the automatically created prefix, and we insert our own suffix, removing parts of the file name and calling it underscore crop. Now we will close all of the images in the Product Explorer window, and we will open only these two subset images. And here we can see the file name that we have given these two subsets. What we will now do is to perform a multi-looking in order to reduce the size of the image. So we go to Radar Multi-Looking, and in this way we also reduce the speckle. So let's select a multi-looking factor of 3x3. Clearly, if we were interested in very high resolution mapping of the flooded areas, we would not do a multi-looking because that would reduce the resolution. But in this case, the floods cover quite a large area, and we're interested in a low resolution map of the flooded areas, so we will apply a multi-looking. And here we will leave the default underscore ML as the suffix. So we'll repeat this process for the other image. And now we will do a calibration. So we will go to Radar, Radiometric, Calibrate. And this will enable us to compare the two images. So here we will leave the default sigma naught, which is the ratio of incident to received backscatter per unit area in ground range. And we will select Run. We'll do that for both the images. Now let's have a look at the images, the calibrated and multi-looked images. So here notice how now we have sigma naught as the name of the band. And if we double click on each, then we can view them. And if we select window tile evenly, then we can view them side by side. Notice how the images appear quite dark. And if we go to the color manipulation window, then we can see that many of the pixels, in fact most of the pixels, have a very low backscatter value, and we have a few pixels with a very high backscatter value. So it would make sense here to convert the pixels from a linear scale to a non-linear, a logarithmic scale. So we call that decibel. So we convert the images to decibel, and then we will have a much better visualization and also a histogram that's easier to manipulate. So here we right click on the name of the band, and we select linear to from dB. And then we select yes to create a new virtual band. And we repeat that for the second image. So linear to, right click, linear to from dB, and we select yes. Now we can view also the decibel, the bands in decibel. And again, if we select window tile evenly, then we can compare them simultaneously. So notice how now in decibel, there's a much clearer distinction between the land and the water pixels. And if we look also at the histogram, we can see a much easier to manipulate histogram. In fact, we can see two peaks here. One peak corresponds to the pixels over land, and the smaller peak corresponds to the pixels over water. Finally, we will do a terrain correction in order to project the pixels onto a map system and also correct for the distortion over the areas of terrain. So we go to Radar, Geometric Terrain Correction, and here we'll select Range Doppler Terrain Correction. Again, we can leave everything as default, so we will use the WGS84 Geographic Latitude Longitude projection. And then we select Run. We will leave the default _TC as the suffix. Now let's have a look at the terrain corrected images. But first we will convert the bands again to decibel. And this time what we will do is we will convert these bands from virtual to actual bands that are written to the file. So here we select Convert Band, again by right clicking and then left clicking to select Convert Band. And then we will save the image by clicking File, Save Product. And this will save the decibel band to the image. And we will repeat the process for the other image. So here we go to, we right click and select Linear 2 from DB. Then we right click again and select Convert Band, and then again we save the product. Now let's have a look at the terrain corrected bands in decibel. So notice how the terrain has been corrected here. We no longer have this distortion, and we can see that the image has been projected onto a map system. We can do a contrast stretch here to highlight only the pixels over the land. Now we can do the same thing with the archive image. And now what we're going to do is we're going to overlay one image onto the other. So to do that, we will create a stack. And given that the images have now been projected onto a map system, we can stack these just using the product geolocation. So we go to Radar, Co-registration, Stack Tools, Create Stack. And here we can select Add Opened and remove the images which are not the final images. Or we could also select the plus icon here and browse to the images we wish to stack, which are the multi-look calibrated terrain corrected images. In the Create Stack tab, here we will select Product Geolocation as the initial offset method. Given that we have not applied precise orbits to these images, the geolocation information is good enough to overlay one image onto the other in order for them to be well registered. If we were to do interferometry, then we'd need to do a much more precise co-registration, but for this application it's enough just to overlay one image onto the other. And here we will, in the Output tab, we will remove the parts of the file name that are not common to both images. So we remove the acquisition date, because here we're going to merge the images together. And then we select Run. Now we can close this window, and here we have our stacked image. And now we have the bands from each of the images put together into one image file. So what we can do here is, let's just open the two images in decibel and again apply a contrast stretch. And what we can do is to overlay the two images in the same viewer and also create an RGB composite of the two images. So here, if we go to Layer Manager and we select the plus icon, and then we go to Image of Band, select Next, and here we will overlay the second image onto this one here. So here we have the 20th of March image, so we will overlay the 4th of September image in decibel. And then we can compare the two by selecting or deselecting this checkbox next to the layer that overlays the original image. Or we can select the layer here and change the transparency slider. Now we're going to apply a technique to distinguish between the flooded areas and the permanent water bodies. And to do that, we will create an RGB composite. First, we select the name of the image in the Product Explorer window, so the name of the stack. Then we go to Window, Open RGB Image Window. We will select the archive image for the red band, and we will select the crisis image for the green and the blue bands. And the reason why we do that is so that in the red channel we will have, over the flooded areas, a high radar response, because these areas will be land. In the archive image we do not expect to see flooded areas, and therefore we will have a high backscatter return. However, over the flooded areas we'll have a low backscatter return in the crisis image. So where we see flooded areas, they should appear in red, as we will have a high response in the red channel but a low response in the green and blue channels. Over surrounding areas where we have no flooded areas, we should see tones of grey, as the backscatter should be more or less the same in red, green and blue. Over the permanent water bodies, we should have a uniformly dark return, given that we will have a low backscatter return in both the archive and the crisis. Therefore, in red, green and blue, we will have a low response. So now we will select OK and view our flood map. So here we can see quite clearly in areas of red the flooded areas. And we see the river, which appears very dark, and then the surrounding areas are different tones of grey. In some areas we may see some parts of the image in cyan, so in the green and blue channels, where we have a higher response in the crisis image than in the archive. But these may be due to a particular ground cover which is not related to floods. Now what we can do with this flood map is to export it to a different format. So we could go to File, Export, and select, for example, GeoTIFF. Or another very quick and simple way of comparing this flood map with other layers is to convert it to Google Earth format, and then we can overlay it onto the imagery in Google Earth. So to do that, we can right-click inside the viewer and select Export View as Google Earth KMZ. And here we can create a file name for this Google Earth image. We can call it flood, and it will save it to the KMZ format. And then once it is finished, we can browse to the folder where we have saved the KMZ file. And then if we have Google Earth installed on our computers, we can just double click on this file and it will open in Google Earth. And here we can compare our flood map with the optical imagery on Google Earth, either by deselecting it here in the layers list, or we can change also the transparency here. We can also check the registration of our image. So if we go to the edge, for example, of the image, we can check the registration, which in this case is pretty good. So this is just a very simple technique for producing a flood map. It's not perfect, but at least it can be carried out very simply and also very quickly. And for disaster management applications, time is often of the essence.